Hi, and welcome back to my channel. So, this is a follow-up video on the Polylogarithmic Hardy Space, which I talked to you about before. So in here, I'm going to talk about multiplication operators and their like, and then talk about sort of the multiplication operators over the Fock space, the Hardy space, and the Polylogarithmic Hardy Space. So right now I'm going to restrict myself to bounded operators to sort of give us a start on where we're going. And so then what we're going to see is that the Polylogarithmic Hardy Space has only trivial bounded multipliers. It actually has trivial density defined multipliers, but that proof is probably going to take a whole lecture on its own. So if you didn't see the last video, let me go ahead and give you a little bit of a recap. So before, I actually had a couple errors in my video, which was pretty embarrassing. So I totally botched the factorization of the zeta function. I lost s somewhere in the mix, and I also had an index wrong at a certain point. And so if you look at the product I left at the very end, that would basically correspond to the product of the harmonic series, which is divergent. And so it actually doesn't really correspond to anything at all. So you need that s in there in order to push it forward. And in fact, s has to be bigger than 1, because if it's 1, your zeta function is a harmonic series, and we know that doesn't converge. And so we know by the p-test and the rest of from calculus 2 that if s has real part larger than 1, then that series is going to converge, and that's more or less where we're stuck. And also, when we talk about Hardy Space as a Dirichlet series, it's not just in the right half plane, which would be where the real part is positive. We actually need to be bigger than the real part being bigger than 1/2, I think. And you get it 1/2 rather than just 1, just through the Cauchy-Schwarz inequality. So when you use Cauchy-Schwarz inequality on one side, you're basically going to be squaring 1/2, and then that's what allows you to talk about it that way. Okay, so those were a couple errors. And then on the actual definition of the polylogarithm, I forgot to put an n on the power of w bar times z, and so that should be corrected there too. But yeah, other than that, everything else was pretty much correct as far as I know, unless you find something, and please do tell me. But yeah, so this is the polylogarithm, and so we're talking about a reproducing kernel Hilbert space, and so this is a space of analytic functions, and where z lives inside of the disk and s lives inside of c. As long as z has magnitude less than 1, s is allowed to run more than just on the right half plane, but it can be any complex number. And so for any fixed z, we actually end up getting an entire function in s, which is really nice, and that is going to be one of the key ideas that goes into the proof of showing that we only have trivial bounded multipliers over the Polylogarithmic Hardy Space. So this Polylogarithmic Hardy Space sort of is a blend of two different reproducing kernel Hilbert spaces: the Hardy Space, which is the collection of analytic functions inside the disk, and so that's basically functions that are, say, f of z is equal to the sum of an times z to the n, where the index runs for n going from 0 to infinity, and z has magnitude less than 1. We saw that the kernel function there is a Zegu kernel. I think I'm pronouncing that right, but you know, I have been known to be wrong. I think it's a Hungarian name, but don't get me wrong. Don't quote me on that. On the other hand, we have another kind of space that is interesting to us, and that is the Hardy space of Dirichlet series. And so in that case, we actually have Dirichlet series, which are basically series that aren't in terms of z to the n, but rather 1 over n to the s, where s is our variable. And so there it's more or less the same thing. It's the sum of n equals 0 to, or n equals 1 to infinity, because you can't divide by 0. Of a sub n times 1 over n to the s, and here in both cases, for the Hardy space and the Dirichlet space, we want the sum of an squared in magnitude to be less than infinity. And so for the Hardy space of Dirichlet series, the ultimate result is that the kernel function, it corresponds to the zeta function, or rather it is zeta of s plus t bar. Now, if we take a look at the Polylogarithmic Hardy Space, it sort of blends the two of these things together. It is it consists of functions that are the sum from n equals 1 to infinity of a sub n times z to the n, and all of that divided by n to the s. So it was a function of two complex variables, and it's sort of a blend between power series and Dirichlet series. Now, the kernel function you have there now is actually corresponds to what is called the polylogarithm, which has been studied by people like Don Zagier and others, and so this is sort of the first sort of function space that's sort of arisen out of it, at least as far as I'm aware. So you can see this space as sort of a blend between these two Hardy spaces, the Hardy space and the Hardy space of Dirichlet series, and yeah, it's interesting to play around with. So now what we're going to be looking at are multiplication operators over each of these spaces, and also over the Fock space, which is a space of entire functions, and I'll give you the definition in the lecture there. So the Hardy space, so let's talk about what a multiplication operator is. A multiplication operator is an operator that corresponds to some sort of function. So you have this little function that is over the same domain as the functions inside of your in your spaces. And so for the Hardy space, these multiplication operators are going to have a symbol or a function that has a domain itself over the disk, and then for the Hardy space of Dirichlet series, these functions need to be over sort of the half plane that corresponds to all the real parts bigger than 1/2, and then for the polylogarithmic Hardy space, we need the function to actually be a function of the disk crossed with the complex plane. And so then basically what you get with these multiplication operators is that now when you multiply a function from your Hilbert space, be it the Hardy space Dirichlet series, or the polylogarithmic Hardy space, the multiplication of a function from that space with phi should end up being in that space itself. At least if it's a bounded or continuous operator, then that's always going to work. We'll get into cases where it doesn't always hold in the next lecture. When you take a look at something like this, you get sort of some ideas that come out of operator theory helping you out here. So you can see that multiplication operators, they actually contain the range of their symbol inside of their spectrum. And so then you know that spectrum itself, if you've had operator theory, and we can go ahead and talk about this a little bit, it is going to be bounded by the bound of the operator itself. And so then that means that every time you have a function that is a symbol for a bounded multiplier, then it turns out that it's actually going to be a bounded function itself. And so, and it turns out that it's going to be just as smooth as the other side of, it's going to be just as smooth as the functions inside your space, or at least to some extent. And so, so when you multiply it over a function of entire functions, it ends up being an entire function itself. When it's a multiplier over analytic functions over a disk, then the symbol itself is going to be analytic over that disk. And so what you can get from that there is that the bounded multipliers for the Hardy space must be at least a subset of the space of bounded analytic functions over the disk. And it turns out that it is exactly that. You can start with the other way around. You take a bounded analytic function of the disk, and you can get back a symbol for a bounded multiplier. And there's a similar concept that happens for the Hardy space of Dirichlet series, and so those are nice. And so then you can say, well, okay, so then if I have a bounded multiplier, if I have a function that is a bounded analytic function over the disk across the plane, is that going to be a symbol for the polylogarithmic Hardy space? And the answer is almost never. And it has a lot to do with what is called Liouville's theorem, which tells us that anytime we have a bounded entire function, it must be identically constant. And this is something it shares with the Fock space, which is why we're going to go over that as well. Okay, so that's going to be the lecture, and so we'll go into details next. And so I'm changing this up a little bit, and so I'm basically going to be putting the actual entire lecture as a hidden video, and you can find a link up here in the corner and also in the description, and I'll also put it as one of my end cards to the screen, just to sort of separate out my hours-long lectures from these sort of intros. And so you'll see this intro copied again over there, but yeah, but if that's enough for you, then have a good day, and no worries, and if you want to learn more, click the link. All right, so I guess we can go ahead and jump into it.